All right, so I'm going to start chapter 10 today, which is second moment of inertia, but I want to do a couple of more centroids before getting to that, and then we'll do second moment of inertia and centroid kind of at the same time. They go hand in hand. But so last time we start doing some practices on centroid, and we talked about, so I think this was the problem we did on Friday. Let me see. Okay, someone asked if centroids are on test on Wednesday. No, test on Wednesday is going to be all the way to the end of friction. Okay, so end of chapter 8. Chapter 9 and 10 are not part of test on Wednesday. Yeah, I was going to mention that at the end. But anyways, so we're talking about centroid. So let's see, what is the equation for centroid y bar? What is the equation for that? All you have to do is flip one page and look at the Friday class. What is the equation for centroid?
Integral of y dA over s dA, or I mean integral of dA.
Okay, someone said in the chat also. It's not y, what is it? It's different than y. It's not y dA, what is it? X? No.
Lambda y.
It's not lambda, it's y tilde. This is called tilde. Okay. It's different than y. All right, so this means summation, right, of infinite number of y tilde dAs. That's what it means, right? Summation of all of that. This means summation of all dAs, right? So what is summation of all dAs mean? What does integral of all dA means? What does it equal to in general?
Just A.
Just A. So this is area, right? Total area. All right. So now let's look at this figure. Sure, I can do an integration. For integration, you have to find two things. You have to find dA and you have to find y tilde first, and then put it in the equation and find it. But this cross section that I'm looking at, it's much simpler, right? I can just have two areas, right? I say, hey, this is two areas sitting like this. So instead of integral, okay, I'm going to call this area 1, and I'm going to call this one area 2. Instead of integral, now that I have finite number, what else I can use instead of integral? So integral was for infinite number, right? What do you use for when you have a finite number of something?
Well, would you just use like a basic area equation then? You don't have to account for like.
No, the question is integral is for infinite number. of anything.
Addition for finite.
Not exactly addition.
Summation.
Yeah, but what is it? What is it called?
Sigma.
Sigma. There we go. You guys are engineer. You should be using engineering language and engineering notation and mathematical notation, right? So sigma is for finite number of anything. So now that I have two areas, is that finite or is that infinite?
Finite.
That's finite, all right? So I'm gonna change the integral into sigma. I'm gonna say y tilde 1 area 1, y tilde 2 area 2, right? I have two of them, over total area, which is also like this, y tilde area over summation of area. This is what it means. I just changed the integral to sigma. Because this area is simple enough, I don't need to do an integration to figure out the area of a rectangle, all right? This one, sure, I didn't know how to do it, so I had to do integration, but this one is simple enough, all right? So let me redraw this quick here. Okay, area 1, y tilde 1, area 2, y tilde 2. So my y bar is summation of y tilde area, summation of area, which is y tilde 1 area 1 plus y tilde 2 area 2 plus, if I had more, over y1 plus area 1 plus area 2. Okay. So now let's figure out each of those terms. All I have to do is find y tilde 1 area 1, y tilde 2, and area 2, and I should be able to find the y bar, right? Okay, so let's see. What is y tilde? Just gonna put my x-axis here. What is y tilde in general? In this equation, when I had integral of y tilde dA, what is y tilde?
Distance from the x-axis
Distance of what?
of the center of area or centroid.
So what is the difference between y bar then? What is y bar? In general, in this general equation, in this equation, y tilde dA over dA. So let's see. I have y bar, I have y tilde, I have dA, right? Those are the three things in this equation. So what is each of them? What is y tilde in this equation? Sorry, I couldn't hear you.
Centroid of dA from the x-axis.
So it's a distance between centroid of that little sliver, right? dA to x-axis. So what is y bar?
Same thing, just from the x-axis.
Same thing from x-axis. Can you say the whole thing?
Oh, the center of area.
Okay, so this is distance between centroid or center of this whole area to x-axis. What is dA?
The area.
Is what?
The area.
Is the area. So dA is area.
No, it's the change in area.
It's not changing area. We discussed all of this on Friday.
It's like a sliver or chunk of the area.
The
It's a
infinitely slim.
differential amount of area. Okay. It's a little tiny sliver of area that we take. Here's the thing. If you do not understand these three things, you are not able to do problems of chapter 9, chapter 10, dynamics, mechanics of material, and machine design. This is what you're going to be using. Machine design, mechanics of material, you use tons and tons of I and Y bar, X bar, IY, IX, which is the chapter 9 and chapter 10. You can ask Colton. Colton has had those. It's important to understand these, and now it's the time to understand it. It's actually not the place to understand. You should learn these stuff in math, you know, in math classes, what does integral means, what is a differential area is, and stuff like that. But if you haven't, now it's the time to learn it and learn it properly, okay? And learn the proper terms, all right? Because you're learning, you're in an engineering education. If you know, it's the time to decide whether I want to be a good engineer or a bad engineer, okay? I just want to have a degree and with a really low quality, or I want to be a good engineer that knows his stuff, all right? So these are very simple stuff, and now it's the time to learn it properly and understand what it means and why do we use that. Do not use Y instead of Y tilde. Do not say area instead of differential amount of area. Do not say distance of centroid to axis instead of distance of, I don't know, area to axis. So try to be precise, try to be good engineers and good students, all right off the bat. Okay, so with knowing that, look here, Y tilde is distance between centroid of dA, because here I have dA, right, to X axis. So what do you think Y tilde 1 is here?
$240 millimeters.
Yes, but I just need explanation of what it means. What is it in general?
Just your Y value.
Okay, we discuss all of this, right? And someone just telling me this is just Y value. So why do you think I bother to put a tilde up there? We just discussed this, right? And I literally told you do not say Y tilde is Y. 5 seconds later, someone says it's just the Y value. So what I want everyone to just read this sentence. Okay. Y tilde is the distance between centroid of that little sliver of area to my x-axis. Here I'm dealing with a sliver of area. So now who can tell me in this equation what is Y tilde? It's not your Y value.
Distance from the x-axis to the center of your sliver of area.
Okay, there you go. So it's distance between centroid, not the sliver of area. I was dealing with a sliver of area. Here I'm dealing with a full area. Centroid of area to x-axis. Is everyone clear? So what about Y tilde 2?
Same thing for the other rectangle.
For the other area, right? So it's distance between centroid to x-axis. All right. Area 1, we know it. Area 1. Area 2 is just area 2. So now I appreciate if someone said the values. Now we can look at the values. What is y tilde 1 then? It's a distance between centroid of area 1 to x-axis. So what is the value here? Now I'm looking for numbers.
300 millimeters.
Okay, so let me see. I have 240 here. Okay, and I need centroid of area 1 to x-axis. Centroid of a rectangle is located in the center of it, right? So it's right there. And this little guy is going to be 60 millimeter. So y tilde 1 is 300 mm. So it's 60 plus 240, 300 mm. Okay. Area 1, that's simple enough. It's 120 mm multiplied by, how much is that?
600. Because you have
480, 600?
120, that's 600.
Yeah, 600.
No,
So
no,
this
just 600 millimeters.
is
Not
600, yes.
Yeah.
480 plus.
Okay. Yeah.
Okay.
Yeah. Euro.
So this one is going to be 72,000. All right. Any questions about y tilde? I know that can be a little bit confusing sometimes.
Where did you get the 600?
This 600, so it's given here. So it's 480, it's 240 plus 240 plus 120. Okay, so let's see. What about y tilde 2? What is that one? The value of it.
120 millimeters.
Okay, so you got to read this sentence, right? It's the distance between centroid of area 2 to x-axis. Centroid of area 2 is located at the center of it, which is half of that distance, so it's 120, yes. Okay. Area 2 is going to be 120 mm multiplied by 240. Okay. 28,800 mm. Any questions about these two? Y tilde 1 and y tilde 2, or areas. Okay, so let me see. I got y tilde 1, I got area 1, I got y tilde 2, I got area 2, area 1, area 2. I'm ready to put everything back in the equation. Okay. Oh, I don't want to write the whole equation again. Y tilde 1, area 1 plus y tilde 2, area 2 over area 1 plus area 2. So it's going to be 72,000 multiplied by 300. Was it 300?
Yep.
Yes. Okay. Oh, this is just mm. Plus 8 mm. This is area. And y tilde is 120 mm. Divided by total area.
And if you add another shape or like another area, you just add on y tilde 3.
Exactly.
Okay.
Exactly. Yes. Yes. How many? So if you can, like this problem that we did, right? For the second part of it, remember we kind of did the same thing because it was one area here and then one area here, area 2, area 1. So you just can kind of build it. If the shape is simple enough, like this one, it's just a rectangle, you can find the area and y tilde, you just add them together like this. If not, then you just integrate them and add them together, okay? So this is going to result in 249 mm. So let's see. So this here is 240. So this is a little bit, it's kind of here. The Y bar.
Do we do it with respect to y then to find x bar, and then you can find the center of?
Exactly.
Yeah.
Exactly. So which for this shape is going to be just here. It's going to be on this line because it's totally symmetrical. Okay. Question, does it matter where my x-axis is? The figure is drawn there and I just moved it down here. Does it matter where the axis is in the centroid of this?
No.
So someone said no, but I'm gonna challenge you. I say, hey, I just told you this is distance between centroid of A2 to x-axis. So how come the distance between x-axis doesn't matter? Or location of x-axis doesn't matter?
That's not what the problem's asking.
The problem is exactly asking that. It's asking y bar, which is the distance between the centroid and x-axis.
Because if you move the axis, it'll, like the centroid will still be located in the same spot, depending on, because your Y bar will change in correspondence to it.
Exactly. So the answer is my value of y bar that I find is going to be different, right? So if I change my x-axis location somewhere else, my y bar might be, I don't know, 50, 60, 70, depending on where my x-axis is. But all of them are the same exact line, right? If I move my x-axis to here, let's see. Let me ask you this. If I move my x-axis in the center of this beam, where do you think my y bar value will be? If my x-axis was here from the beginning, it's in the center. What is my value of y bar do you think will turn out to be?
Negative 59 millimeters.
So it's going to be 50. So this whole thing is 60. So it's going to be 60 minus 49, right? Or negative or positive, whichever you look at it. So the point is, if I don't want to confuse you, the point is, doesn't matter where you pick your x-axis, the centroid of this shape is always going to be here. Your value might change is because you're moving your axis around, but the centroid is always going to end up at this point right here. Okay. Questions?
So you get the same location, just a different value depending on where your starting
Exactly.
point is.
Exactly. Because you're going to measure your y bar and y tilde 1 and y tilde 2 from different locations. Yes. Okay. All right. Let's look at another problem. Find reactions at the fixed support A. So this is something from chapter 4, chapter 5, right? So a rigid body problem. Find the reactions at the fixed support A. Okay. What is the first step in doing rigid body diagrams? Step 1.
Isolate an outline.
Exactly. So the first step is to draw a free body diagram, right? Free body diagram has the 3 steps: isolate, outline, active forces, reactive forces, right? So let's do that. Step 1, this is the beam, and then I put active forces on there, which is this distributed load, and I'm gonna find the equivalent force. Okay. And then reactive forces. What kind of reactions does a fixed support have?
X and Y.
And moment.
And moment. Fixed support does not move in X, does not move in Y, does not rotate. So it's going to be AY, going to be a AX, or the other way, doesn't really matter, and a moment. Okay. So that's the first step I got to do. I got to do a step 0, or if you want to call it step 2, I have to find FR and X bar. In the problems we did in chapter 4 and chapter 5, it was always really easy, right? It was like usually a load like this. You just found it, replace it. If they wanted to be like super crazy, they would probably put a triangle on top of it too, right? But what about here? Here you can't just find an area. So let's just kind of remind everyone, what is FR in terms of words? What does it mean, FR?
Resultant force.
Okay, well, in this problem, what does it mean for us? What should I
Total
find?
force
Your load
of your
at one force.
Sure, but what again, what should I find to find FR?
The area.
The area, exactly. So FR is area under loading. I mean, all the answers were correct, but I was just looking for like the meaning of. So if I find area under this curve, this area, right? That's my FR. What about X bar?
Where the force is like located at, or you want it to be on the free body diagram.
Yes, but what does it mean? Use proper engineering
The
terms.
distance from the x-axis. The distance of the force from the x-axis.
Okay, still not quite what I'm looking
Sorry, the
for.
y-axis, my bad.
Distance of the centroid from the Y.
Centroid. Centroid of area. Okay, but you're correct. That's the location of FR to Y axis. But that's the center of this area with respect to Y. Okay. So what I just found for this problem, I just found centroid of this area, right, with respect to X or to Y axis. Here, if I find centroid of area, if I find area under loading, I find my FR and X bar. All you have to do is write equation. Okay. Pretty much if you do the centroid, you can find the area too, because it has this one in it, right? So let's do that. We got to find 2 things. Let me go back here. Something you have to do, absolutely have to do, is draw this element of your area. Think of it as a free body diagram. Don't just draw it on the figure and stuff like that. Okay. So I got to find 2 things. I got to find X tilde, and I got to find dA. Tell me first in words, what is X tilde? Distance between what?
Centroid and the y-axis.
Centroid of what?
centroid differential area.
Okay, it's not the centroid of the area. It's centroid of the sliver, that little differential amount. Centroid of dA to y-axis, yes. And dA is just differential amount of area, right? So this is my dA. Centroid of this one to y-axis. Which is going to be same as my x. Okay. Why do I tell you that, hey, don't say x tilde is same as x? Here's an example. You can take a sliver of area any way you want. What if I take my sliver of area this way? Now what is the x tilde for this problem?
Y bar.
X tilde. X tilde is what? Distance between centroid of dA to y-axis, right? Centroid of this is right here. This is my x tilde. So what is the x tilde for this situation here?
Is it just half the length of your DA?
Which is what? So let me go even back further in math equation. Forget about load, force, statics, anything. You have a curve, you have x, you have y. I take a point in this curve. What are the coordinates of this point? If this is point 1,
XY.
x and y, right? So it's xy axis. So this point is x1 or x, doesn't matter. This point is y or y-axis. It's the value on y-axis. This is the value on x-axis, right? So when I draw a sliver like this point, how much is this point, this length?
Just X.
Just x. How much is this length here?
Y.
Y.
Okay. So let's look back here. What is this length here?
Y.
Y. What is this length here?
X.
Okay. So you see the difference? That's why I keep telling you guys right here, x tilde is different than x, y tilde is different than y, because not always they equal. So in this case, this is x tilde equals x. In this case, x tilde equal x over 2. Okay, so they're not always the same thing, and you cannot always just automatically replace x tilde with x or y tilde with x. It depends on the orientation of elements. One thing I always usually do, is I draw my element parallel to the axis that I want. So in that case, I don't need to worry about it. So this one is parallel to y-axis. If it's parallel to y-axis, then x tilde is x. If it's parallel to x-axis, then y tilde is y. See that's the difference. So anyways, x tilde is x here. My dA is just dx multiplied by y dx, because this length here is dx and this length here is y. All right, so let's put it back in the equation. X bar equal x which is dA, which is y dx over y dx. Okay. Can I do this integral or no?
No.
Because of the variable, right? So my variable is dx, but I have a knowing y in here. So I have to replace the y. So by the way, this problem, I should have used w. It's just the axis. So this is y. So let's change this to y. Okay. Just to avoid confusion. I should have used w and x or x and y and y. So just the notation was off a little bit. So let's do this. Y, I have to replace my y here. 3, 1 minus x2 over 25 dx. 3, 1 minus x2 over 25 dx. One more thing I got to do here. And our bounds of integral. What are the bounds of this integral here?
0 to 5.
0 to 5. That also is related to x. How much x moves? X goes from minimum of 0 to maximum of 5. So 0 to 5 units are meters. Okay. So this integral will give you 18.75 over 10. Okay, messed up on the units. The units are, this one is okay, so they're not. Okay. And that one is also area, so kilonewton over meters. There you go. Okay. So this will give you 1.875 meters. What about my force? Did I find that? Which one is my force here? The FR that I was after.
It'd be the denominator, so 10.
10, right? It's my area. This is area under loading. So my force is 10 kilonewtons. I think I have everything that I need for my free body diagram. So now it's easy. Summation of forces in x equals 0. I'm back to my equilibrium. Okay. AX is 0. Summation of forces in y equals 0. Anything that points up is going to be plus. I have minus 10 kilonewton plus AY. AY is 10. Okay. And finally, summation of forces above point A being 0. Summation of moments above point A being 0. I have moment at A, and that goes with my direction, so that's a plus, minus 10 kilonewton. Location is 5 meters minus 1.875 equals 0. This one here is 5 minus 1.87. And that's going to be oh wait, this is also plus. FR creates a moment in the same direction. Okay. Now we got it. 31.2 kilonewton meters. What does this negative mean here, by the way?
Rotating clockwise.
So the one I drew here should have been the other way, right? Okay. Questions? So now you guys can do any distributed load, regardless if it's just a rectangle or a simple triangle, or it has any shape or any equation. I think I have another one here that we can do next time. But I want to quickly get into mentioning the second moment of inertia. Questions about this? About centroid or equations or y tilde or area or integration or anything? Okay. So we have about 10 minutes. I don't know if we can get to an example or not, but because I promised, we're going to start on this one. So determine the moment of inertia for the shaded area about the x-axis. What do we show the moment of inertia or second moment of inertia with? What letter do we use? I want to know how many people watch the video, lecture video. What is it? Sorry.
I.
I. Okay. It has an equation. All right. Oh, it's y2, sorry. Not y tilde. Okay. What does it mean? Again, for people who watch the lecture video, what does I mean?
Inertia.
Yeah, but what does it mean? So here's what I mean by that. Like force, you can have a physical understanding. Force is how much you push or pull on something, right?
The resistance to rotational movement.
Not exactly.
Inertia has no physical meaning.
Exactly. So it has no physical meaning. Doesn't mean anything. All right. You cannot define it the way we define force or moment. Moment, we say, hey, it's a tendency for rotation. Friction, we say, is a resistance against movement. Tension, you can understand it. Compression, you can understand. This one doesn't have any physical meaning. It just used a lot in fluid mechanics, in mechanics of materials, and all of that. So they were, when you look in those courses and those topics, or if you watch my lecture video, or if you read the literally first page of chapter 10, it proves to you that, for example, to find moment or amount of force on a floodgate, terms will show up in the equations y2dA. In mechanics of material, if you want to find a stress on a cross section, this we're going to show up. Okay, so this term started showing up everywhere. So they decided to give it a name to simplify the equation. So instead of MC over integration of y2dA, because this was a property of area, they just simply say MC over I. Okay, so it doesn't have any physical meaning. It's a property of area, but we're going to use it, and we're going to see how we will use it and stuff like that. Okay, so it is called second moment of inertia. Or second moment of area about an axis. Okay, or moment of inertia. To just confuse you even more, inertia, it's not inertia. Okay, this term again came from another term here. This is inertia. They say, hey, these two look awfully similar, so let's call this one inertia too, and confuse people even more. It's not inertia, it's just the name of it. Okay, so don't get confused by the name. It's a property of area, okay, that we're going to find and we are going to use. problems like this, all right, I'm gonna start this one, but we're gonna finish it. So moment of inertia, shaded area about x-axis. That means I, x. Y to the area. If it was about y-axis, it would have been I, y. The only difference is instead of y2, then we have x2 dA. Okay. So this is much simpler. All you have to do is find dA, which all of you should know by now is just the differential amount of area. Okay. Or just that little tiny sliver of area. Okay. Important. For Ix, choose your dA parallel to x. For Iy, choose your dA parallel to y. You don't have to, all right? You can choose any area you want, but this is much, much, much simpler, and it saves you a lot of trouble and a lot of confusion, all right? So for this problem, I'm going to choose my area parallel to x-axis, a little tiny sliver of area, which again, it could have been y tilde 2, but in this case, doesn't really matter. Okay. It's again the centroid or the area to x-axis, and this length here is dy. So my d area is y dx. Okay, so let's just put it back in the equation. y2 and my dA is y dx. Okay. Oh, why did I put that? It's y dy. Sorry. There we go. So it's just going to be y3 dy. What are the bounds of integral here? Can someone tell me?
0 to 8.
0 to 8. Why not 0 to 4?
That'd be the x-axis.
That would be the x-axis, right? So the variable is dy. So we care about how much dy is moving. This dy that I have starts from 0, goes all the way to 8. So 0 to 8. I hope everyone knows how to do that. Okay, I messed up here something. No one caught it. My dA is, and that's where the confusion comes from. My dA is, what is my dA? What is my mistake here?
Isn't it 2y? Because
No, this is dy. But what is length of it?
It should be x dy.
Should be x. Okay, that's my mistake right there. My dA is width multiplied by length, so it's x dy. There we go. Sorry about that. It's x dy. Okay, so my x is given by 1/8. So my y is going to, my x is going to be 2y 1/3 dy. Here's y. y is equal 1 over 8 x3. So 8y equals x3. So x equals 2y over 1, 3. Okay. I'll finish this one on Friday, but just if you are curious and you want to finish it, this is right here. I just want to start this chapter so you guys can, if you want to look at lecture videos, practice problems, stuff like that, you're able to do it. Okay. Wednesdays, so we don't have lecture. It's exam time, and it's just so chapter 9 and chapter 8 are not part of. Chapter 9 and 10 are not part of it. So Centroid and moment of inertia are not part of it. Don't worry about those. It's all the way up to the end of friction. Okay. Any questions you guys have, I'll be happy to answer. Otherwise, you guys are good to go.